So now that the background information is out of the way, let's talk about, or rather the course overview and logistics are out of the way, let's talk about some background on concurrency and parallelism in Java. I'll start out by giving you some definitions of the terms, and these are things that may show up on the quiz on Wednesday, which will be very short, by the way. So let's talk first about what is concurrency. So concurrency is essentially a form of computing where threads, which we'll define in a second, can run simultaneously. So that, of course, begs the question, what is a thread? Well, a thread in Java is essentially a unit of execution that can run streams of instructions concurrently or simultaneously on one or more processor cores. So if you take a look at this picture here, you see this kind of grayish round angle. That's a process, which is a unit of protection and resource management. And inside that process, there can be one or more threads, and that's what the little squiggly thread-like symbol is with the arrow. The arrow is the instruction pointer. And you can have these things running. There could be multiple of them. And then you can have the threads will be mapped by the operating system and the virtual machine and the hardware and so on onto the various processor cores. And these are processor cores, right? They're Apple cores, so they're processor cores. And in Java, at least, you go ahead and create a thread by saying new thread and giving it some computation to run. And this is actually using the Java 8 Lambda notation, which we'll talk about later. Concurrency is typically used to offload work from some main thread, or typically the user interface thread in a GUI program or a mobile program. It offloads work from the user thread to one or more background threads. So we might have a user thread that's displaying various widgets and other UI components to the display, to the screen, and that might be this thread. And then if we have long-running operations, things that may be downloading files or making network communications or balancing B trees or whatever they're going to be doing image processing, that computation, those computations can run in so-called background threads. And the way this works is the background threads are able to block. They can afford to wait for stuff. They can wait for images to download, or they can wait for locks to be released, or they can wait for other things. But the user interface thread does not block. So the user interface thread remains responsive, and the background threads do the blocking. So that's a very, very common use case, very common scenario in concurrent programs. And we'll talk a lot about this, and you get a chance to play around with it. Concurrent Java threads can work with each other. They can interact with each other via shared objects and/or message passing. So shared objects basically allow you to synchronize the operations of multiple threads on objects such that the state of the object remains coherent after each operation. So we'll talk a lot about this. This is a huge topic in the course. We'll typically have something like a lock of some kind or a monitor object of some kind, and we'll have locks that guard access to what's called a critical section. Critical section is a piece of code where only one thread can be running at a time, typically because we want to make sure the state doesn't get corrupted. We'll talk more about that later. And so you have locks that essentially mediate access to the critical section. One thread at a time can be running inside the critical section. Other threads that want to access the resources in the critical section block, awaiting their turn. And that's called a shared object. So you can share objects. And these are just basically Java objects. They're shared between the multiple threads. So that's one way to do things. Here are some examples of Java synchronizers. We will cover pretty much all of these things in the class. We have so-called synchronized statements and methods, reentrant locks and intrinsic locks. We have atomic operations, semaphores and condition objects, compare and swap or CAS operations, and so on and so forth. And you'll find I tend to like visualizations of stuff. So when we talk about reentrant locks, we typically talk about mutexes for mutual exclusion. So we'll talk about restrooms in airplanes being an example of mutual exclusion. When we talk about things like semaphores and condition objects, we're talking about coordination. You're passing control from one thread to another, so it's kind of like handing off a baton in a race. When we talk about atomicity, it's sort of all or nothing. It's kind of like the transporter beam in Star Trek, where you really want to beam everything in one fell swoop. You don't want to get half of somebody beamed one place and the other half stuck someplace else. So we'll talk a lot about that, and I'll always try to give you sort of human metaphors to think about these various technical concepts. So that's essentially shared objects. The alternative paradigm is called message passing, and this is where messages, a message or messages are sent from a producer thread or threads to a consumer thread or threads via some kind of thread-safe queue. So you typically have one or more producer threads that are putting stuff into the queue, and you have one or more consumer threads that are pulling or taking stuff out of the queue, and you communicate by passing messages from one thread to the other. So that's another way of interacting between Java threads. There's lots and lots of examples of thread-safe queues. So we have array and linked blocking queues. Your first programming assignment has a piece of the implementation that you just have to know exists. You don't have to know really how it works. That uses an array blocking queue. There's priority blocking queues, synchronous queues, concurrent linked queues, and so on and so forth. It goes on and on and on. So there's lots of cool stuff that are used to move stuff back and forth through queues. And you'll get a chance to play around with a lot of this. Irrespective of whether you're doing interactions with shared objects or message passing, some of the key goals are to be able to share resources safely and efficiently. Safely meaning not corrupting stuff. Efficiently meaning not taking too much time, too much overhead, and to avoid various kinds of concurrency hazards, which we'll talk about briefly. You can take a look at this link to find more examples of things that will cause trouble. One of the common problems you run into when you start sharing stuff, especially with shared objects, is you run into something called race conditions. And race conditions are a hazard that can occur when a program's behavior depends on the sequence or the timing of the threads in order for it to operate properly. And the typical way that race conditions rear their ugly head is by having multiple threads simultaneously accessing the same pieces of data without using the proper protection in the form of synchronizers. And when this happens, the things get corrupted. The various threads crash into each other and cause all kinds of problems. We'll talk a bit about that. Very, very common problem. Race conditions are a very common problem in concurrent programs. If you're not really that familiar with race conditions and concurrency, you might want to try running this little sample. This is a test program called Buggy Queue, and as the name suggests, it basically induces race conditions due to the lack of synchronization between producer and consumer threads that are using a bounded queue. So it doesn't have the proper locking mechanisms in place, and so when you run it, it'll do very strange things and blow up. Another problem you run into commonly when you start trying to work with concurrent programs are what are called memory inconsistencies. And this is a more subtle problem than a race condition, although they often manifest themselves in very similar ways. And the basic issue here is if you have a modern multi-core processor, the cores that are running in the hardware typically have their own caches. And that's by design. It's meant to speed up access to variables that reside locally. And that's all well and good. But the problem is when you start sharing objects between threads that are storing their data in caches, you can have problems because the data in one cache isn't properly synchronized with the need to access it in another cache. And that's because those caches are basically local snapshots of this global memory space. And so memory inconsistencies occur when you don't use synchronization mechanisms properly, and you think you're accessing a variable that has one value, but instead it's actually reading something that's out of the cache and not properly flushed through in order to be able to give you the right global perspective on what the values are. So you get inconsistent views of the same data. We'll talk a lot about that. A very subtle point. It's not easy to understand because it requires you to sort of think at a hardware level as opposed to an abstraction level. The good news is that the mechanisms that fix race conditions typically fix memory inconsistencies as well. And I always like to use the metaphor of transporting people around. You want to have these be atomic operations. For those of you who are Harry Potter fans, it's much the same problem when you disapparate and you, splinch? When like your ear ends up in one place and your arm ends up in someplace else, right? So you've got to figure out a way to do that consistently. Yet another common problem that occurs when you start writing concurrent code is what are called deadlocks. And that occurs when two or more competing actions are each waiting for the other to finish, and thus no one finishes. And here's a very simple example that shows the problem. Here we have two threads, thread T1 and thread T2, and they're trying to coordinate on two locks, L1 and L2. And the problem here is that T2 owns lock L2, T1 owns lock L1, and then T2 tries to get L2, T1 tries to get L2, and T2 tries to get L1. Well, that's going to lead to deadlock because both threads are trying to grab someone else's lock, which is locked, and therefore neither of them will actually get their resources consumed. And we'll talk a little bit about deadlock avoidance later. All right, so that was basically an overview of concurrency. So remember the key points of concurrency for allowing some things to run in the background, and then sharing and interacting with other threads through message passing or shared objects. The next topic, and by the way, almost everything we're going to talk about in this course relates to concurrency. The next topic is parallelism, which is also a very important topic and getting increasingly important, especially as we move into a world of data science and big data, where you have large amounts of information you need to process as quickly as possible. So parallelism is a form of computing that performs several steps on multiple processor cores. So here are our cores again. And basically what it does is it first takes some big task and it breaks it up into a bunch of subtasks. So the big task might be searching the web, right? So if you're doing a Google search, you want to search the web. And that is done in practice by taking that request and then so-called sharding it by having the request run on lots and lots of computers, each of which search a piece of the internet, right, or a piece of the web content. So that's the idea of partitioning a task into subtasks. And we often talk about forking the tasks. We'll talk about that later. And then once you've got things forked, you go ahead and run these subtasks in parallel. So each of the subtasks will then run in parallel on various cores. So now they're all running literally in parallel simultaneously. And then finally, after we get a bunch of results, we then combine the sub-results, which come from that parallel computation, to form a single final result. And that's sometimes called joining. So you may have heard about things like MapReduce or fork join frameworks. Those are what are going on there. We're taking a big task, breaking it up into pieces, running all the pieces in parallel, getting sub-results, and then joining all those sub-results back to get one final result. The key goal of parallelism is to efficiently partition the tasks into these subtasks, do the processing in parallel, and then combine the results back together. So the key is efficiently. And if you do it well, you get a big speed up. If you don't do it well, you've made yourself a lot of extra work for no gain. So the key goal of parallelism really is on optimizing performance. So throughput, scalability, latency, and so on. And for those of you who've ever seen the movie This Is Spinal Tap, it's kind of like cranking up the volume to 11, right? You want it to run really fast and run really well. In contrast to concurrency, which is really about sharing resources safely and efficiently and avoiding hazards, right? So concurrency is a lot about sharing of resources. Parallelism works best when there are no resources to share, where there's no mutable state that's being changed. Mutable means change, so we're not changing state, and when we don't end up having to have the threads block for any length of time. So that's when it works best. You can still use it if those conditions don't hold. You just have to be very careful. So avoiding shared state is crucial. Whoops. Therefore, if you learn more about Java 8, and we won't talk a whole lot about that in this class, although you can learn more about it by watching last semester's lectures or coming back next fall and taking the class that'll talk about parallelism. There's a lot of discussion in Java 8 about fork join and work stealing. And the whole goal there is to be able to avoid having to block and keep things running as quickly as much as possible. There's an excellent tutorial by a guy named Brian Getz, who's a Java architect from Oracle, and he talks about how Java has evolved over time from a focus on concurrent programming to parallel programming. And basically, his point is that as the number of cores has increased, right, so we've got lots and lots and lots of cores now, we really haven't managed to get as much speed up as we would have liked. And that's because people really had a hard time figuring out how to program concurrent programs. And so Java 8 focuses on parallel programs using something called functional programming and streams and so on. like I said, we won't talk too much about that in this class. That'll be covered in next fall's class, or you can go back and watch the videos from last semester. Okay, so that's a quick overview of Java concurrency and parallelism. So now that you have a little overview of what concurrency and parallelism are, let's kind of focus in and talk about how Java supports these concepts. I've given you a really high-level view of that, but let's kind of delve into it a bit more. So in this discussion, we'll talk about the history of Java concurrency and parallelism, how it's evolved over time. You might know some of this already, you may not. It's okay if you don't know it. And then I'll also kind of summarize everything by talking about which mechanisms for concurrency and parallelism to apply and when, and which ones you need to understand. So if you want to make a choice, you have to choose between multiple competing options. What would be your decision criteria? Let's first start by talking about a little history. So this goes back to the middle 1990s or so, some 20 plus years ago. When Java first came out, it had foundational support for concurrent programming. And the features it provided were Java threads, which you'll get a chance to learn about in the first assignment, and something called built-in monitor objects, which you'll learn about later. And that was what was available when Java shipped in 95 or so, whenever it first hit the streets. The main focus was on very basic multi-threading and synchronization primitives, and you'll get a chance to play around with a lot of these things. Here's a simple example. We have a simple blocking bounded queue. Let's assume, for sake of argument, this is implemented correctly, unlike the buggy queue I talked about before. And what we do here is we make an instance of a blocking queue that's bounded. We then create a pair of threads. So this is, the first thread will be a producer thread, and it's going to write messages into the queue. The second thread will be a consumer thread. It'll read messages out of the queue. And then we go ahead through this array of threads, and we start each thread. So now the threads are up and running. And then we go ahead and wait for them by joining with the results in order to get the results, or in order to wait for the things to be done. And while they're running, they're passing messages back and forth between the threads. By the way, this gives you a little hint for your first programming assignment, which looks somewhat like part of that. This is how you start and join with threads. The other concept that was provided in the early versions of Java was this concept of a so-called built-in monitor object. So this is built into the programming language. It's part of Java, the language, as opposed to Java, the class libraries. And it provides support for basic mutual exclusion, or mutex properties, which mean only one thread at a time can be in the critical section, and coordination primitives, which means allows you to take turns and schedule the execution. So here's a simple example. Here's a method from our simple blocking bounded queue called take. The semantics of take are you're going to block until there's something in the queue, and when there's something in the queue, you can take it. You can retrieve it and go on your way. And the way that works is we use a synchronized statement, which says only one thread at a time can be in this critical section, which is everything between the opening curly brace and the closing curly brace. So we're going to synchronize on this. That's called the intrinsic lock. We'll talk about that more later. And with the lock held, while the list of messages is empty, we're going to wait. And what wait does is it basically says, I can't make any forward progress, so please put me to sleep and don't start me up again until there might be something in the queue I could take. So while we're waiting, another thread could come along and put something in the queue, in which case it would wake up this thread, which would then reacquire the lock, loop back around, check to see if the list was empty. If it wasn't, we would come through here, notify anybody who might be waiting for the queue, to be not full, and then we go ahead and retrieve the item off the list and return it. So these mechanisms, synchronized blocks or synchronized statements, are mutual exclusion mechanisms, and wait and notify all are examples of coordination primitives. So those were some of the things that were available in the early versions of Java. So the good news was it was very efficient in the sense that implementing this code doesn't take a lot. It's built into the virtual machine and the operating system and the underlying hardware. These mutual exclusion mechanisms typically use hardware primitives and so on. But it's also low level and limited in its capabilities. So it's got accidental complexities. What that means is if you get confused and you do things the wrong way, your program will stop working, and it's tedious and error prone to figure that out, right? So accidental complexities are problems that arise from limitations with software techniques, tools, and methods, as opposed to inherent complexities, which are properties of domains, right? Something is hard because it's just fundamentally hard. This is hard because people didn't do a very good job of designing the features as we might like. And you can read more about the concept of an accidental complexity at that web link, which talks about a famous paper by a guy named Fred Brooks called No Silver Bullet. And he talks about inherent and essential complexities, or inherent versus accidental complexities in software design. This is what we had in Java for about 8 years or so. Then in around, I think it was 2004 or so, they came out with Java 1.5 or JDK5. And that added a whole boatload of new concurrency and synchronization mechanisms. So we have things for managing pools of threads called the executor framework, a whole glob of synchronizers like reentrant locks and condition objects and semaphores, which you'll get a chance to play with. We also have things like various barrier synchronizers and so on. They have a bunch of blocking queues. We kind of talked about that before for passing messages back and forth between threads. There are a bunch of atomic classes for atomically incrementing integers and longs, working with various types of booleans and so on. And there's also preliminary support for things called concurrent collections, things like hash maps that can be accessed from multiple threads. So that added a whole bunch of cool new features into Java, and that appeared kind of at this level. The focus with Java 1.5 was on so-called coarse-grained task parallelism. You can read more about task parallelism down here, where the computations could run concurrently on one or more cores. So one of the classic examples was something called the executor completion service, which allows a piece of code to submit tasks to run, and those tasks are essentially put in a queue, and a pool of threads inside the executor completion service will pull the tasks off the queue and run the tasks in parallel. And as the tasks complete, they're then put on something called a completion queue, which is also managed by the executor completion service. And then the application that submitted the tasks can have one or more threads pulling the results out when they're done. So it's basically a kind of a way to have a pipeline of submitting work that runs in parallel and then getting the results back. So that's one of the features, one of the cool features that's available in Java 5. They also provided a bunch of support for interesting synchronizers, such as barrier synchronizers. You get a chance to play around with a lot of this stuff in the class. So here's an example from a variant of the programming assignment we've got, where we created a fixed size thread pool to run a bunch of beings, and then we have barriers which will wait until all the beings are created before letting any of them run. And then we also have another, that's called a cyclic barrier, and then we have something called a countdown latch, and that's used to not let the main thread continue until all of the threads in the pool have finished their current processing iteration or cycle. And so this is just a way of coordinating the starting and stopping of a group of threads. So you'll get a chance to play around with some of these features later as well. Java 5's capabilities are very feature-rich. There's lots and lots of expressivity and power. They're also highly optimized to work efficiently on multi-core processors and hardware. However, they're a bit tedious and error-prone to program. You have a lot of work to do. So it's very important to understand patterns and other techniques to do this stuff correctly, and you'll get a lot of chance to play around with that in this class. With Java 7, which I think probably came out maybe in 2010-ish, don't quote me on that, but it was around that time, they created something called the fork join pool, which is a really interesting data parallelism framework that allows a task to be run on different elements in a large data set. So you've got a task, you can split it up into subtasks, and each subtask takes a different subset of the data and then goes ahead and runs the processing in parallel. So each subtask, we split until the subtasks get down to a certain size, and then we run each of those subtasks in parallel on the underlying processor cores. and when they're all done, we join all the pieces back together. So that's often what's called data parallelism or MapReduce style model or fork join programming and so on. There's lots of interesting examples on my website. You can take a look here. One of them basically searches in a big corpus of files containing the works of Shakespeare, and it goes and looks for phrases. And it basically creates a fork join pool and goes out and runs the searches on all the different works of Shakespeare in parallel using that approach. And it's pretty cool. This is a very powerful technique. Fork join framework is highly optimized. It's used for lots of other stuff. If you program with Scala or Akka or Kotlin, you're using the fork join framework under the hood because it's a very powerful and scalable way of being able to do concurrent processing or parallel processing. However, it's a bit tedious to program directly. There's a lot more work you have to do by hand than you might want. So it's unnecessarily complicated. So to address that with Java 8 or Java 1.8, depends how you want to count it, they came up with the concept of parallel streams in order to be able to make it easier to use the fork join framework. And there's also something called completable futures, which also uses the fork join framework. The focus in Java 8 is on functional programming for data parallelism. So again, it's a bit out of the scope right this second to talk about functional programming, but functional programming is basically a way of being able to express your computations in the form of so-called lambda expressions or method references, which are more functional in nature. And if you do it right and you set your data structures up to avoid having to share, because after all, parallelism is all about not sharing mutable state, you can go ahead and have really expressive code that will take input collections or input streams and then process them through a pipeline of so-called aggregate operations. So we might have some URLs come in, we might filter out URLs that we've already cached, the ones that we've not yet cached we might download, then we might go ahead and apply various image processing filters to the downloaded files or the downloaded images, and then we could collect the results into a list. So this is an example of functional programming in a data parallelism model with multiple threads, and Java 8 streams and parallel streams makes it really easy to express things in this form. Something else that's provided in Java 8 is support for asynchronous reactive programming, which is another very interesting programming paradigm. And this involves running computations asynchronously. So if anybody here has ever worked with JavaScript, you may be familiar with the JavaScript concept of futures or promises. And so basically what you can do is you can go ahead and start some operation, like you might download a web page, and that runs in the background. And then as the web page is downloaded, in other words, when the operation completes, you could then have some other computations go out and count the number of images in the page. And you might have another operation that runs in parallel that goes out and crawls all the links in the page to find more images. And when all those things get done, you could then combine them together in order to get a final result. And the whole thing is done in a very asynchronous and reactive way. So that's another capability that's provided in Java 8. There's an example here called Image Stream Gang that applies asynchronous programming data parallelism programming for managing images. And then there's also one that does it with completable futures. And you can see that they're both very similar looking, but this does synchronous parallel computing, and this one does asynchronous parallel computing. Really cool, very powerful. We're not going to talk a lot about those mechanisms in this class just because that was the focus of last semester. I'll cover it in the fall, or as I mentioned, you can go back and watch the videos. Really, really cool stuff. One of the nice things about the parallelism support that's available in later versions of Java is it strikes a nice balance between programmer productivity, in other words, writing correct code efficiently and quickly, and good performance. And that's the right balance to try to strike, often. However, the problem with these approaches, the problem with the higher level ways of programming, is that they are sometimes overly prescriptive. So if your problem fits within the Procrustean bed of the abstractions that are provided with Java 8 parallel streams and completable futures, life is good. If you're writing code that doesn't fit within those Procrustean boundaries, then it may not work so well. So it kind of constrains you in ways that may not be appropriate. Okay, so that leads to the last part of this discussion in this lesson. When should you apply these different mechanisms, and which one should you take time to learn. Obviously, it's good to learn them all, but when would you apply different ones? One thing to note is that these mechanisms are available at multiple layers in the software stack. So we won't talk too much about this in this class. I'll probably give you a little bit of an overview later when I talk more about Android. But modern software platforms are designed in a layered manner. Surprise, surprise. So you'll have things like the operating system kernel, which is typically written in C, which accesses the hardware. You have various system libraries like libc, which are typically written in C or C++. You have execution environments like the Java Virtual Machine or Dalvik and Art, which is Android's execution environment, sort of like the Java Virtual Machine. You have various concurrency and parallelism frameworks, threads, and synchronizers. Now we're getting up into the Java world. You have application frameworks, you have applications, and so on. And different capabilities lurk in different layers in modern systems. So when would you choose which approach? Well, if you're writing lower level classes or you're writing performance sensitive apps, in other words, apps where the right answer delivered too late becomes the wrong answer, or one where you're like gaming, for example, where you want it to be as efficient as possible because you want to have real-time interactive experience by the users, then you're probably going to want to use the very efficient Java shared object mechanisms. And we'll cover a bunch of those, right? Semaphores, reentrant locks, monitor objects, concurrent hash maps, condition objects, and so on and so forth. And so those are sort of the core, most fundamental ones. And they're very, very efficient because they're implemented in a way that lurks just on top of the underlying operating system and hardware mechanisms. And if you are curious about this, take a look at this video, which talks about the design and implementation of the Java util concurrent package, which is very cool. So the good news is that these mechanisms are efficient and lightweight because they're very, very carefully tuned to the properties of the underlying hardware. The downside is that they're a bit tedious and error-prone to program, as you will discover when we program them. So it requires you to understand various design patterns and various programming techniques to do it right. Let's talk about message passing. That's an alternative way of doing things. So framework developers, people who are building frameworks for others to use, such as Android developers at Google, they often like to use message passing mechanisms. So a good example would be the Android async task and hammer frameworks, which we'll talk more about later, which are used to pass messages from background threads to the user interface thread and vice versa. So that's a message passing mechanism. There's also the Java executor completion service that we just talked about a second ago. So those are ways of passing messages back and forth. The good thing about message passing is it's very flexible and decoupled because the producers and consumers, or the senders and receivers of the messages, don't have to know too much about each other. They communicate in a very decoupled way by passing messages back and forth. And that's good in the sense that it makes it easy to write things that are not tightly coupled with each other by sharing objects, which often makes stuff very brittle and hard to change. The downside is when you start passing messages versus accessing these shared resources through the lower level mechanisms, it adds additional time and space overhead to your program. So they typically will not be as efficient as the approaches that use the shared object style, but they'll be easier to write and easier to think about and easier to compose. So there's trade-offs, right? Classic trade-offs between productivity and performance. Yet another perspective are people building mobile applications, or really applications. And again, depending on how their programs are designed, they may end up wanting to access these higher level frameworks, things like Java 8 parallel streams or completable futures, RX Java, some of the Kotlin mechanisms that are available, and so on, fork join pool. So these are higher level frameworks, and they make it really easy to program if your problem conforms to what the framework provides. And those of you who took the class last semester recognize this. This is our web crawler program that used all kinds of cool Java 8 concurrency mechanisms to download images and process them. So the good thing about these higher level frameworks is they're very productive and robust. Again, it makes it easy to write code quickly. It makes it easy to write code quickly that will be correct if you follow the rules because they do a lot of the heavy lifting for you under the hood. The downside is there's probably even more time and space overhead, which may or may not matter, but you have to be aware of it. And they tend to be overly prescriptive in the sense that if your problem fits them nicely, you're in great shape. If not, then it's going to be an awkward Procrustean bed-like mismatch. The key thing to remember, and this is especially important when you're at this stage, right, is as you get further on in your career, you'll undoubtedly specialize in something, and you'll be an expert at one of these layers, or maybe a couple of these layers. But the highly regarded full-stack developer, right, people who know how to program up and down the entire stack of layers, are well advised to understand the concepts and mechanisms at each of these layers, right? Especially when you're in student mode, right? It helps to understand it all. Eventually, you'll end up deciding where you want to focus, but it's good to get that broad perspective. Okay, so that is the end of the background section.